In this example, we're going to look at the following 3x3 matrix. What we're going to try to find is the row space and the column space of the 3x3 matrix. A is equal to, first row, 2, negative 3, 1, second row, 5, 10, 6, and third row, 8, negative 7, and 5. Now with that in mind, there are two possible strategies. So in the first case, what we do is we break down the matrix A into either row matrices or column matrices for the row space and the column space respectively. If we were to refer to those rows as, say, x1, x2, and x3, or those three columns as x1, x2, and x3, what we could do is set up c1x1 plus c2x2 plus c3x3. Yes, technically these would be vectors, so let's give them little vector symbols. And set it equal to a generic vector in R3, something along the lines of, I don't know, vector y. Then figure out if we can get any constraints on the variables that we use for y. The other thing that we can do is find a basis and write a linear combination of basis elements, or basis vectors. Now, since this is supposed to be an instructional video, we might as well set up one of each and see how it goes. So let's start with the row space. So as far as the row space is concerned, what we would be doing is setting up c times the vector 2, negative 3, 1, plus c2 times the vector 5, 10, 6, plus c3 times the vector 8, negative 7, 5, and we're going to be setting that equal to a nice generic looking vector that we'll refer to as y1, y2, and y3. Using the same delightful strategy that we've been using for quite some time, we're going to load each of these vectors into our matrix as columns. Now, what you'll notice here is that all that we're ending up with to the left of the augment is simply the transpose of the original matrix. And this will represent C1, C2, and C3 in terms of the coefficients. Then when we augment, we'll include a column for y1, a column for y2, and a column for y3, which means that our augment is going to be the identity matrix. I'd like to take this down to reduced row echelon form, and in order to do so, I'm going to be making use of the calculator. Calculator is an awfully big help on this one. So enter the matrix menu, head over to edit. We're going to edit ourselves a 6 by, nope, that's not right. Try that again. That's a 3 by 6, not a 6 by 3. So first row, 2, 5, 8, 1, 0, 0. Second row, negative 3, 10, negative 7, 0, 1, 0. And 1, 6, 5. It doesn't look right. 1, 6, 5, 0, 0, 1. Alright, I think something may have gotten messed up there, so I'm just going to double check real quick, make sure that everything got in here correctly. 2, 5, 8, 1, 0, 0, negative 3, 10, 7, 0, 1, 0, 1, 6, 5, 0, 0, 1. Okay, I think we're good. Now we'll go ahead and take this down to reduced row echelon form. So select RREF for the matrix A, and let's see what we get. Yikes. Math. Enter. Enter. Let's get some fractions in here. Super. Alright, now the big important thing that we get out of this is going to be in the last row, because the last row is what I like to refer to as the constraint row. That is because to the left of the augment we see nothing but zeros, implying that we're going to have an equation of the form linear combination of y1, y2, and y3 is equal to zeros. So that's 1, 1/4, negative 5/4 from that last row. And again, the rest we don't really need because we got our constraints that we need. So we can interpret this as the row space of A is equal to the set of all vectors of the form y1, y2, y3, such that, and then interpret this constraint, y1 plus 1/4 of y2 minus 5/4 of y3, that's got to be equal to 0. Now, again, this is just a representation of the row space. If we wanted to get a basis for the row space, what we would do is figure out what row echelon form of the matrix A looks like. Any non-zero rows that we get there will be basis elements. Now, the nice thing about what we just did is there is a nice shortcut for this. Heading back into the matrix menu, if you edit your 3x6 matrix down to a 3x3 matrix, crap, that's the transpose. Well, never mind, I guess we're going to have to redo this anyway. 5, 10, 6, 8, -7, 5. I suppose I could have asked for row echelon form of the transpose of that matrix, but no worries. Now, whether you go for row echelon form or reduced row echelon form is completely irrelevant. You're allowed to go for either one. Your calculator may even give you a different result than what my calculator just gave me. So, this row echelon form is 1, -7/8, 5/8, 0, 1, 1/5, and 0, 0, 0. That means a basis of the row space of A would be the following two vectors. 1, -7/8, 5/8, and 0, 1, 1/5. Writing a linear combination of these two vectors would give you the representation of the row space as well. Now, the one thing that I'd like to point out is that if either of these vectors got plugged into this equation, we would wind up with an identity. And that is because if we were to take 1 plus 1/4 of -7/8 plus, minus 5/4 of 5/8, we would in fact get 0. And if we were to take 0 plus 1/4 of 1 minus 5/4 of 1/5, we would get 0 as well. So these basis elements do correspond to what we see here as well. Now, the other thing that row echelon form tells us is the basis of the column space. So for a basis of the column space, it is the first column and the second column that correspond to where our leading ones are. Leading one here and leading one here. That means that if we go back to the original matrix, those two columns will represent the basis elements of our column space. So first column is 2, 5, 8. Second column is -3, 10, -7. So for a basis of the column space, we could say 2, 5, 8, and -3, 10, -7. What we've really done here is just created a minimal spanning set of all of the columns of the matrix. In terms of a representation of the column space, if you were interested, just like we talked about here, we could start by setting up a linear combination of the columns of A. However, a linear combination of the columns of A is just going to wind up looking exactly like A. So for an actual representation of the column space, what we'll be setting up is C1 times the first column, which was, oh boy, now I gotta go back and forth, 2, 5, 8, plus C2 times, I think it was -3, 10, -7, but I'm going to verify that, and then C3 times, I think it was 165, yeah, 165, -3, 10, -7, so 165. Once again, we're going to be setting that equal to just a generic vector in R3. We'll call it y1, y2, y3 once again. So in terms of an augmented matrix, we'll be using exactly the matrix A, as we did before, and augmenting with, once again, the identity matrix. Taking this down to reduced row echelon form, and interpreting any rows of zeros to the left of the augment is going to be our key for success on this one. So we've already got the right entries there, so we'll just throw a 1 here, a 1 here, and a 1 here in the 1, 4, 2, 5, and 3, 6 entries. Then we'll verify that everything looks as it's supposed to Looks good. We'll take that bad boy down to reduced row echelon form to get our representation of the column space. RREF of the matrix A. Oh man, keep forgetting to do that little math enter enter thing. Oh boy, there is a lot going on in that last row. So we got a 0, 0, 0 to the left of the augment, which is what was expected. Then we got a 1, 2 23rds, and negative 7 23rds. Holy wow. So the representation of the column space that we can use, call space of A, is going to be equal to the set of all vectors of the form y1, y2, y3, such that y1 plus 2 23rds of y2 minus 7 23rds of y3 is equal to 0. And I would imagine that if we took our two basis elements from the other side and plugged them into this equation, we would wind up getting identities from both of these as well. So yeah, those are the two different ways that you can figure out a representation of the row space or the column space of a matrix.